Okay, cool. Lance is calling from Florida. Welcome, Lance. I grew up in Florida, Orlando. Don't hold it against me. I can't tell you how many people tease me about that. All right, Samia, I think we can get started when you're ready.
Awesome. Hello, everyone. Thank you for joining us from different parts of the world and different time zones. Let's begin. So my name is Samia. I'm a software engineer at Microsoft. I work on building tools for Azure customers in the GitOps and cloud native space. Here we are cloud native at SF, a San Francisco-based meetup focused on CNCF projects. Today we are doing a showcase of 4 popular incubating projects at CNCF. For those of you who may not be aware, incubating projects are a specific maturity level designated by CNCF based on adoption rates, a healthy rate of changes, and contributors from multiple organizations. So should we jump into our first speaker? Josh, do you want to, should I hand it back to you?
Yeah, let me share. Our sponsor for today is Acuity, and Acuity is the enterprise company for Argo, founded by the co-founding engineers of the Argo project. I highly recommend. I think most people know who these folks are. So I will drop the link in for this, and we have some swag, which is awesome. So every third person who signs up will get a prize. And yeah, so thank you, Acuity. Really appreciate the support for the community. And I'll turn it back over to you, Samia.
Awesome. Thank you for sharing that. And thanks, Acuity. Let's jump into our first talk. I'm very excited. Our first speaker today will be talking about KEDA. KEDA is a Kubernetes-based event-driven autoscaler that allows you to scale your workloads based on events, even proactively scaling your containers before any impact is done, which is pretty cool. I'd like to introduce Jeff Holland from Microsoft. Jeff is the Director of Product for Azure's Platform as a Service and Container Platform. He's a current maintainer and co-creator of KEDA alongside Yaron, who's also on the call, and others. Jeff is the Azure spokesperson for serverless and cloud native apps. So without further ado, I'll pass it over to you, Jeff.
Great, awesome. Hopefully my audio comes through great. I turned off my video just to save my bandwidth. So I'm currently traveling right now, so I'm in a hotel. So we'll jump into it because we only have a few minutes and there's a ton of exciting projects I want to make sure that you can all hear about. So as was introed, I'm going to be talking today about KEDA and how KEDA helps you scale any workload better. As was mentioned, just a little bit about me. So Jeff Holland, currently working in Azure at Microsoft. My team's helping build a few services, including Azure Functions, Azure Websites, a new service called Azure Container Apps, which is actually powered by some of the tech here, including KEDA and Dapper. And then I'm a current maintainer and co-created KEDA along with Yarn and a few other folks to help with event-driven scale. So let's jump into it. What is KEDA? Why do we need it? And to answer that question, I actually want to tell a little bit of a story. Well, not really a story, like go through a thought experiment with you all, okay? So let's imagine that we're all going to a huge party after this. It's going to be in person. All 33 of us show up, 34 of us now. And the question is, okay, Jeff, you're in charge of bringing the pizza. And so the most important question that I need to figure out is what is the right amount of pizza to bring to the party? Now, there are a few different ways that I can figure this out and make sure all of us get a piece of pizza. One strategy might seem a little bit weird, but go with me here. I'm going to decide how many pizzas I need at the party by staring at the pizzas on the table and watching when they are eaten, if they are eaten, and how quickly they are eaten. That's the only signal I'm going to use to make my decision. So the party starts. I don't actually know how many people are coming or not. I come and set one pizza out on the table and I watch it. 10 seconds later, all the pizza is gone. Every slice was taken and eaten. So I'm like, okay, what do I know? Well, I know I'm definitely going to need more pizzas. It was eaten fairly fast, so I can guess there's at least 2 or 3 people at the party because I don't think one person could have eaten a pizza in 10 seconds. So I go to the next step and now I bring out 2 more pizzas and I set them down and then I just stare at those pizzas. Both of those pizzas end up getting eaten. Pizza 2 in 20 seconds, pizza 3 takes a little bit longer. So I still don't know a whole lot. I know I need more pizza. Maybe it was slowing down on that third pizza because people were starting to get full. Maybe people at the party were just confused into why the pizza seems to be growing in this sequence. I don't know. So I continue this process, bring out 4 more pizzas, then 8 pizzas, whatever, until finally I'll land at the answer. Maybe the answer is 14 pizzas was the right amount of pizzas to feed everyone at this party. Now, I got to that answer, but it took me a while. And it took me a while because I was doing this really weird way of bringing out a pizza and watching it and then bringing out more. So maybe it took a whole hour before everyone finally got fed. Now, if we were really having a pizza party and you were in charge of bringing the pizza, no one would ever use this strategy to figure out how many pizzas to bring. In fact, they would probably just do one very simple thing, which is asking how many people are coming to the party. And you get the answer to that. Oh, 100 people are supposed to come to the party. Cool. I know if 100 people are coming, I'm probably going to start by ordering like 10 or 14 pizzas. I'm going to get pretty close to the right answer from the get-go just by asking that question. And the reason why is because with this strategy, I'm making my decision based on the cause, which is how many hungry guests are going to be there, rather than the symptom, which is how many pizzas are eaten or how quickly they're eaten. So I can get to the answer much quicker. Everyone gets fed much faster. Now, as silly as this example might seem, the reality is that for a ton of our applications, we actually scale our apps much closer to strategy 1. You deploy your app, you deploy your container, and then you watch, oh, wow, this is eating a lot of CPU. This is eating a lot of memory. So I'm guessing we need more replicas. We need more instances. So I'm going to add a few more, and then I'm going to watch. Okay, now 2 of them, all their CPU has been eaten. So now I'm going to add 2 more, and so on and so forth. So this is traditionally how applications scale. It's not super efficient because we're scaling on those symptoms. So KEDA at its core helps you scale any container in Kubernetes based on the cause of the work and not the symptom of the work alone, which would be like CPU and memory consumption. So those causes can be a lot of things. How many unprocessed messages are there in a queue or a Kafka stream, or how many database records need to be processed? If I know there's 1 million messages sitting on a queue that aren't yet processed, I know just from that signal, I probably need to scale a few replicas, even without waiting for CPU or memory to get hit. So KEDA is an open source component, as was mentioned, a CNCF incubation project. You can configure it in any cluster, and it will help you scale your workloads based on dozens of different causes, event sources, okay? So let's show a quick demo of this. I have here a Kubernetes cluster. It's fairly empty. All it has right now is a RabbitMQ queue, and that queue is actually entirely empty right now. Now, the other thing that I have running in this Kubernetes cluster is a deployment, which is a container that consumes messages from that queue. And you might notice it's actually scaled to 0 right now. Now, this is one nice thing that KEDA does for me. It knows that that queue is empty, so I don't even need to spin up this container at all. It doesn't even need to consume one of my cores because there's no work to be done. If this container was running, it would just be sitting there idle. So KEDA has noticed there's no work to be done, and it's driven Kubernetes to scale it all the way to 0. Now, on the other side, if I come in here in this, sorry, my my Zoom thing is in my way, so I can't see my screen. Okay, I'm going to now apply this job, which is going to publish 1,000 messages to that queue. And actually, even before I finished typing the command to watch the pods, it started publishing messages to the queue. And you'll see right away, I now actually have another pod, which is one of these RabbitMQ consumers. So messages started dropping on that queue, and KEDA instantly saw it, and it scaled up 1. But you can see, even as I'm talking, there's not just one consumer instance that's scaled up. There's thousands of messages on this queue. So now KEDA has driven Kubernetes to scale me to 4. Now it's to 8, and so on and so forth. This will continue to scale out horizontally as queue messages got published and as I wait for them all to be consumed. If I waited on this screen long enough, you would see it scale out to an eventual number, maybe 16. Like here, I'm keep scaling out. I'm going to drain the queue. I'm going to drain all the work, and then it would scale all the way back down to 0 because the queue is empty. So that's the kind of behavior here where I'm getting much faster scale. If I would have done this just based on CPU and memory, I might have been sitting here for a really long time for that queue to drain. but KEDA made it much smarter. So how did it do that? Well, first I installed KEDA itself. That was pretty simple. Here, let me go ahead and stop this to save my bandwidth. But the other thing is when I install KEDA, I get this custom resource thing called a scaled object. And this is just a really simple piece of metadata that I deploy or apply to my cluster that tells KEDA, here's the thing I want you to scale, the scale target. In this case, it's that RabbitMQ consumer. And then I tell it what's the event I want it to scale on. How many hungry guests are there? And in this case, it's like, look at RabbitMQ, look at this queue. And I even have this thing here called queue length. Queue length lets me define how quickly it scales. If I set this number very high, that means a lot of queue messages can be consumed by one instance. So it will scale very slowly. If I set this number to 1, it means if I have like 30 messages on the queue, and queue length of 1, it's going to try to target 1 message per instance. So it's going to try to scale me to 30. So I just apply this little bit of metadata, and you can see there's a few different config things here too, which is how frequently should I check for events? How quickly or how slowly should I scale to 0? Do I have a maximum scale? And so on and so forth. And then KEDA does the rest. I won't go all the way into architecture here to make sure we have plenty of time for questions, but KEDA deploys its own metrics adapter, which it then integrates with Kubernetes' own autoscaler. The main thing I want you to take away from the architecture is that KEDA itself does not take over autoscaling in your cluster. It's not saying, hey, throw out all of the stuff Kubernetes does for scaling already, but rather it extends the default autoscaler and just makes it smarter about 30 different event sources. So you can install KEDA fairly unobtrusively. Maybe 90 of your deployments don't use KEDA and 2 of them do use KEDA. It's cool. It's not going to get in the way when you don't need it. It's just going to be publishing these metrics about queues or whatever else for your instance. I'm looking at the time. I know we started a little bit late. I want to make sure we save plenty of time for other projects though. So here's a list. I grabbed this last night from the KEDA landing page of the different event sources that KEDA knows how to do that event-driven scale for. You can see there's everything here from RabbitMQ to Kafka to Redis to AWS event sources, Azure, Google, Alibaba, MySQL, Postgres, Prometheus, a ton. And the community continues to contribute more. And you can even write your own customized scaler. So we have a few users who maybe have like a very custom event source in their own organization. They've written their own custom scaler and connected it with KEDA so that they can get this much more responsive and much more accurate scale heuristics using KEDA itself. So if you haven't tried out KEDA, it's fairly easy to get going with, as I mentioned, based on the architecture. It's fairly unobtrusive. It's just extending through its own metrics adapter, through these built-in scalers, and then this controller loop to help pull in those event sources and publish them to Kubernetes Autoscaler. And so that's the main thing I wanted to show here in just a few minutes. We're really excited. It's now an incubating project. We'd love for folks to join our community. We've got bi-weekly stand-ups. There's a Slack channel. You can engage with us on Twitter, whatever it is. If you have questions, if you want to contribute, please join. We'd love to have you. And with that, I'll stop sharing my screen and turn back on my camera and see. I see we've got like 2 questions.
Great job, Jeff. I'm pretty hungry right now. The pizza analogy was pretty extraordinary. I'm just teasing you. Thank you. That was great.
So I'll answer. Yeah, it looks like. Do you want me to just answer these 3 questions in the queue really quick, and then we'll go to the next project?
Yes, I think we can do that.
Yep. So does KEDA support Kafka consumer lag monitoring for scaling? Yes. So the Kafka scaler does have, in the same way that I had queue length for RabbitMQ, Kafka uses lag to determine how much to scale. So you can say like, hey, if there's a lot of lag between where my current checkpoint is and where my stream is, then I want to scale faster. If there's not a lot of lag, I don't. So it does integrate with lag today. Is Azure Functions still KEDA? Is what Ravi asked. Oh, and I'll mark this one done. So Azure Functions integrates with KEDA. One of the reasons we created KEDA, and even that I was on the founding board, is because a lot of what we learned from scaling serverless functions influenced how we built KEDA. So yes, you can use Azure Functions with KEDA today. In fact, there's a public use case of a customer of ours named PureFacts, who's using KEDA plus Azure Functions to run Azure Functions on Kubernetes and on premises not just in the Azure cloud. So you can use Azure Functions with KEDA, but you don't have to use Azure Functions with KEDA. It's just one of the things that it can scale. You can scale whatever you want. And the last one here, any thoughts on when KEDA HTTP Autoscaler will be refactored? So there is a project, and Hugo must be paying attention to the community. We have a current, I think it's classified as a beta project called KEDA HTTP, which is an add-on for KEDA that lets you do scale to 0 and scale to n based on like requests per second metrics, based on HTTP metrics. I know it's actively being worked on. There's some folks at Microsoft that I'm working with who are doing it. I believe the plan is that in the next few months, KEDA HTTP should graduate to a standpoint that is production ready. So it is actively being worked on. I don't have a more specific timeline than that. But Hugo, if you want to reach out to me on Twitter or something, I'm happy to connect you. And the last one, because this is really short, you can run KEDA in production. It's 2.0. Incubation is a status in terms of CNCF project maturity, I guess. It's nothing to do with production readiness. So KEDA was 1.0 in 2019 or 2020, 2.0 in 2020 or 2021. A lot of folks using it in production. If you go to keda.sh, you'll see a bunch of logos. So you can be sandbox and still production ready. You could be incubating and production ready. It is production ready. So that's it. I'll pass it over to our next fantastic maintainers and presenters.
That was a great talk, Jeff. Thank you.
Thank you so much, Jeff. You definitely got me thinking about the algorithms for serving pizzas in a party. So I'm going to think about it next time we do that. Yeah, thank you so much. Our next project and speaker will be Yaron, who will be talking about Dapper. Dapper is a set of building blocks to ease distributed application development that helps simplify microservice connectivity. It provides you with APIs that abstract away the complexity that developers encounter when building distributed applications. So I'd like to introduce Yaron Schneider, who is a co-founder and CTO of Diagrid, an early stage startup that focuses on cloud native APIs for application developers. Prior to DataGrid, Yaron was a principal engineer at Microsoft, where he co-founded the CNCF projects, KEDA and Dapper, while also serving as a lead architect for Azure Container Apps, a serverless containers cloud service. So without further ado, I'll pass it over to you, Yaron.
Thank you. And great to see you, Jeff. This is the first time we've seen each other since I left Microsoft 5 months ago. So I think we should be meeting more, actually.
I agree. I agree. Great to see you too.
Yeah. Awesome presentation as always. Let me share my screen and let me know when you can see it.
Yep, we can see.
All right. So let's get right into it. What is Dapper? Dapper is a set of APIs. When you come to think about it, it's a set of APIs that's helping developers focus on their business logic and their IP and the code that they actually need to deliver when writing their line of business applications, instead of focusing on infrastructural concerns. And so Dapper has this set of building blocks that are really APIs that are exposed via HTTP and gRPC. And because these APIs are just plain old HTTP and gRPC APIs, you can use Dapper from any programming language, really. So Go, Node, Python, any programming language that understands the HTTP stack, really. Dapper also has lots of integrations with different frameworks like ASP.NET or Django, but at the core of it, and it also has SDKs, but at the core, if you can understand HTTP, you can talk to Dapper. Dapper's building blocks are many. We'll talk about some of them today. So service-to-service invocation allows developers to discover and invoke different services in their cluster reliably and securely, because Dapper will make sure that the communication's encrypted and there's retries. State management is an API that allows developers to save and manage state at scale. And it adds a bunch of features that developers usually look for, like concurrency management and state management, and publish and subscribe is an API that helps developers create event-driven architectures. So if you just want to publish a message, let's say you want to publish your pizza delivery status, because we're extending on the pizza example that Jeff put earlier, Dapper will help you basically create an event-driven architecture where developers don't really need to think about things like consumer groups or partitions. You basically just publish an API call to Dapper with your payload, and Dapper will make sure that it's reliably delivered to your end service. Resource bindings and triggers is a building block that allows Dapper to trigger your application whenever an external event happens. So think something like a Twilio event or a message coming off of Kafka even, or a function that's being invoked. Actors are a very specific programming model that I'm not going to talk about today because this requires probably its own talk, but it's basically a way to distribute compute and state together at very high scale that's really applicable to gaming and IoT edge scenarios. So Dapper has an actor model that's applicable to many programming languages. Underlying all of the Dapper APIs are observability. So you don't have to write your own telemetry stack. You don't have to instrument your code. You just use the Dapper state management, pub sub bindings, or service to service invocation APIs. And Dapper will basically make sure that your entire call graph is actually visible and monitored, and it'll hook it up to whatever monitoring stack you're actually using. So it can be Zipkin, Jaeger, or it can be a cloud native service like AWS X-Ray or GCP Stackdriver or Azure Application Insights. Dapper also gives you an API to connect to different secret stores. So it's a really consistent API where you can just hook up your application to any secret store like Azure Key Vault or AWS KMS, but developers get a consistent API that they can use to fetch secrets. This is especially useful in Kubernetes scenarios where instead of needing to come up like with your own custom solution to mount secrets on your pods, your application code can just call its local Dapper sidecar and Dapper will fetch the secret for you. And if you're writing a multi-cloud architecture, then this of course becomes easier because Dapper integrates with many types of underlying implementations. Configuration is a building block that really allows you to be notified whenever a configuration item changes for one of your applications. So if your app needs some sort of configuration to get started and get bootstrapped, Dapper can give you that and also provide you with a really easy watch API that you don't have to write or maintain. You basically tell Dapper, hey, notify me whenever a configuration item for my application changes, and Dapper will make sure that it's reliably delivered to you. Dapper can run on any cloud or edge infrastructure, meaning it doesn't have to be containerized. It can just run as a local process, which I'm going to show in a sec, on your machine, whether it's Mac OS, Linux, or a Windows machine. And it can also run on Kubernetes using a regular operator pattern with Helm charts that can be deployed. And of course, since most clouds have Kubernetes offering, then Dapper runs really well on most major clouds. So the architecture that Dapper utilizes really the sidecar architecture. If we think about our application, we have it here on the left. We have the Dapper sidecar as a separate process. Like I said, it doesn't have to be a container here on the right. And the app basically just uses native HTTP and gRPC to talk to the local Dapper sidecar. So this is an example of how an app would discover and invoke a different application. This is an invoke method where we're saying, hey, Dapper on localhost, please invoke a method called cart, an application called cart with a method of new order. Now, this exact piece of code can run locally on my machine, and I can then just take it and deploy it to Kubernetes or hook it up into console for service discovery or to any other environment. And this code will basically run in multiple environments, and Dapper will make sure that it's secured and monitored. This is an example of how state management API operates. So we're telling Dapper, hey, Dapper, go to the state store called inventory and fetch me item 67. This is an example of a publish operation where we're telling Dapper, hey, use the shipping pub sub to publish a message to the orders topic. And this is an example of the secrets API where we're telling Dapper, hey, go to this component called Key Vault and fetch me the password. In terms of architecture, you basically have the app calling Dapper over its API. So developers really get consistent APIs they work with, and depending on the environment you're running in, operators and developers can basically set up Dapper using YAMLs to use all sorts of state stores and pub subs and bindings. So for example, if you're running locally, you might want to use something like Redis for your pub sub and state store because it's very easy. And if you're then deploying your code to AWS, you can just switch out that YAML to use AWS DynamoDB or Cosmos DB on Azure or Firebase in Google Cloud, while your code remains pretty much the same. Same thing for pub sub bindings, secret stores, configuration management, and all of the other components. So the components is really a centric piece to how Dapper operates. This really allows you to abstract most of the cloud native systems using these APIs. In many cases, Dapper also adds capabilities to these native implementations that you won't normally find in the implementation itself. One good example of that is a concurrency setting to Redis. So for example, open source Redis does not support first rate wins or last rate wins. So if you have two applications, let's say service A and service B here, that are both running to Redis, the latest call to the Redis key will basically be the one that overwrites the value. But if you wanted something like e-tags, Redis doesn't support that. But Dapper actually has this feature that's applied to all of its state stores. So with Dapper, using Redis, you can get this feature which you won't normally find on Redis, or even some of the state stores here. Same thing for PubSub. Dapper has a feature, for example, to allow you to basically put security policies on top of your PubSub. Let's say you're using Kafka and you want to make sure that service A can only publish to topic A and service B can only subscribe to topic C or D or E. You can do that with regular Kafka, but using Dapper, you can just turn that feature on and Dapper will add it on top of the underlying Kafka implementation. So in many cases, Dapper will actually add more features to the underlying implementations. As far as community momentum, we're really excited to see large participation from many contributing organizations, of course, Microsoft, where we started this project. And then Dapper has a steering committee today that's comprised of Microsoft, Intel, Alibaba Cloud, and Digrid, which is my own company. And we're basically steering the project, and we're seeing lots of new up-and-coming organizations contributing to Dapper. And one of the most exciting things about these contributions are that we're seeing application developers coming in, Dapper's written in Go. So we're seeing developers who are in their day-to-day job writing Java and C# and Python and JavaScript coming in and picking up Go from the very beginning just to extend Dapper, to add features that they need to make Dapper really useful for them. So for me as a maintainer and steering committee member, this is really exciting. And this is why we've been seeing and still continuing to see a really big uptick in the amount of contributors that are coming to the project. We have a Discord channel. I really recommend that you join it. And of course, talk to us on GitHub. So let's take a look at a really quick demo. I'm going to have a React application that's running locally. I'm going to show you how to run Dapper locally in this case, but this entire code, if Dockerized, can just be moved to Kubernetes or even other container orchestrators. So we're going to have a React app, and we're going to publish a message about our pizza delivery. So we're going to publish how many pizzas we want to deliver to the party. And oh, by the way, this is new. This wasn't coordinated with Jeff. And the React app is going to call into the Dapper instance. The Dapper instance is going to make sure that the pizza delivery order gets reliably transferred into our Node.js subscriber through a pub sub that we configure. So let's take a look at our code here. The first thing we'll want to do is install Dapper. So I just downloaded the Dapper CLI. I have it locally running on my machine, but I don't have the Dapper runtime installed. So the first thing I'm going to do is just do Dapper init, and that's going to install Dapper locally on my machine. It's going to download the binary and set up a few containers for our local development experience. So this is done. And what we can see here, if we do Docker PS, is see that we have Zipkin and Redis. So Redis is also a state store and a pub sub. This is pretty useful for getting started locally, but I can switch this out to any of the locally supported implementations for whatever I want to use. So if you go on the Dapper docs, for example, you can see that we have pub sub brokers. So for this example, I could basically just install Kafka locally, go to this Kafka site, take the Kafka YAML implementation, just replace it, and Dapper would work against Kafka, and my code would remain the same. For this example, though, we're going to use the default Redis PubSub component that's installed with Dapper init. This is what the component looks like. So this is a regular CRD. It's going to work locally in self-hosted mode, but later on, if I just want to take it to Kubernetes, I could just take this YAML, apply it to my Kubernetes cluster, and it would work, of course, while changing the Redis host and Redis password. So I have Redis running locally, and this is a pretty regular YAML file. We can see that the pub sub is Redis here, and we have all the metadata that we need. So how does my code look like? In terms of the subscriber, this is it really. I have a pretty simple Node.js app. I have an Express web server, and I have two endpoints. One endpoint is for me to subscribe. So once the Dapper sidecar starts, it'll call into my app. And here I'm basically telling Dapper, hey, Dapper, I want you to create a new subscription, and I want you to subscribe to a topic called A with a pub sub named pub sub. So if we go back to the YAML, we can see here, this is the name of the pub sub. If we have multiple pub sub, we can tell Dapper to subscribe to multiple pub subs. So if I have Redis or Kafka, we could have multiples of these. And the route, which I want you to send this event when it comes in, is A. So I have another endpoint here, which is a post endpoint. It's listening on this A URL here, and this just prints out the message. So this is a pretty regular subscription. You can also subscribe declaratively using a CRD, but you can also do it programmatically. I think most Dapper users actually like to do it programmatically on Kubernetes locally, but on Kubernetes, you'll probably want to do it declaratively. So this is pretty simple. You see, I have no SDKs. I have no tie-in into one particular technology. All I'm telling Dapper is, hey, register to this pub sub and deliver me the message via regular HTTP. And I'm working against Redis. And if I were to publish this to AWS, I would just change this to the AWS schema. On my React server, it's pretty simple. My React UI backend is going to call this endpoint here, which is publish. And I have the publish URL here. So I'm just going to take the order that's arriving, and I'm going to say, hey, Dapper, on localhost, publish a message to the pub sub endpoint and publish it to the topic of my choice with the request body. So pretty simple. It's just an HTTP post that we're issuing to Dapper to just publish the message. So let's see what this actually looks like. First, I'm going to be running the subscriber. The order doesn't really matter here, but I'm going to use the Dapper CLI locally to just help me run the Dapper sidecar and run my Node.js app. This is a helper method. It's going to launch the Dapper sidecar first and then my application. So this is really useful for local development. And I'm going to do the same thing for my React app. So I'm just going to do the same thing and run my React application. The log level here is a bit more verbose, but basically what I said is, hey, Dapper, run this app ID called React form, and here is my port. And then I'm just starting my application. So now I have two Dapper sidecars running with two different applications, one for a Node subscriber and one for a React app. And now I can go back into here, and this is my React application. We're going to publish a message to topic A, and I'm going to say pizza count 10. And I'm going to submit this. I'm going to go back here, and we can see that the application printed that it published the message. And if we go to our subscriber, we can see that Dapper conceived the message and delivered it to the application. So under the hoods, Dapper created the consumer group and the partition count, and it's making sure to insert retries and everything to make sure that the whole business is reliable. And you could just take this code and bind it against really any PubSub provider and just deploy it to any infrastructure and use whatever infrastructure is best for the environment that you're running it on. One last thing, you'll notice that we don't have any instrumentation in our code. We don't have any way to instrument monitoring here. It's just plain old HTTP. It's free of any dependencies whatsoever. But if I go locally into my Zipkin instance, and I'll just refresh this and go to dependencies, I can see that Dapper has actually traced my two applications. So it figured out, even though the message is transferring through a pub sub, that our React form was actually calling into the Node subscriber. And I can basically see that we have 3 calls here. The other 2 calls are me testing this demo beforehand. And we can take a look at the traces here. We can run the query, and we can see all of the metadata, what's the status code, the protocol, the topic that was published to, and of course, the latency. So Dapper works with Zipkin, but it also works with the OpenTelemetry protocol. So again, we didn't have to do any work in our code to actually hook it up into tracing. The only thing you need to do is decide which monitoring stack you want to use. So if you want to use Xray or Stackdriver or Application Insight, you just need to configure those with a simple YAML with Dapper, and Dapper will just make sure to deliver all these messages to the actual backend of your choice. And I think I'm at time, so I'm going to stop sharing here and take questions.
Awesome. So I think you ran out the clock on that, so we'll have to go to the next one. But we'll say, we'll save the questions for the end. And thank you, Yaron. That was great. That was content dense, which we love. So thank you for that. And Samia.
Yeah, thanks a lot. Thanks a lot, Yaron. Now we will be going over to our next speaker. And before I do that, I'll be transferring over to my co-host, Chakra, who will be co-hosting this event with me.
Thanks, Samia. I think the next topic would be a nice segue from application runtime into more of application identity and then authentication. So it's our presentation today. So our next host is Ryan Turner. He's a software engineer from Seattle, working on workload identity and authentication primitives for backend services and jobs at Uber. He's also a maintainer of Project SPIRE and very active contributor from late 2019. So without further delay, I'll hand it over to Ryan. Ryan, take it over.
Thanks. Yeah, excited to talk to you all today about secure workload authentication with SPIRE. So more and more, we've been re-architecting applications to look like this. We have broken down these monolithic services into microservices. And eventually we get to a state where we have a pretty complex web of services which need to communicate with each other to achieve different business goals. And so the challenge we have when we have a rich microservices architecture in terms of security is how do we make sure that all these requests that are flowing between these services are strongly authenticated. So recently, there's been a lot of discussion about this concept of zero trust networking, where essentially you declare the network in your backend infrastructure to be untrusted. And so you don't necessarily trust that any given request that happens in your backend is actually coming from a valid source. So if we can strongly authenticate all of these requests, we have a much higher confidence that there's no one who's accessing these services that shouldn't be. So what is SPIRE exactly? So before we talk about SPIRE, we have to first talk about SPiffy, which is a set of open source specifications that define some identity primitives and authentication primitives. So SPiffy itself is also a CNCF incubating project. It stands for Secure Production Identity Framework for Everyone. And at a high level, it defines a few different concepts about identity. It defines how workload identity is represented. And so there are a couple of different forms of representation here. One is just a string representation of what is this actor represented as, and that is called the SPiffy ID, which is essentially a structured URI format to represent the workload's identity. It's like a name essentially for the workload. And then that identity needs to be like present in some sort of cryptographically verifiable document in order to actually transmit that identity over a connection or a request. And that part of the specification is called the SVID, which stands for Secure Verifiable Identity Document. And that's just like a document format. So the ones that are supported today in the specification are X509 certificates and JSON Web Tokens. And then after we've defined like what an identity looks like, we need to define like how do workloads actually get this identity. So this is a specification called the Workload API, and I'll talk about that a little bit more later. And then identities naturally are kind of grouped together in different organizations or departments. And there you might want to declare different trust boundaries between those identities. And so there's this concept of a trust domain, which logically groups these identities. And in practical terms, that's essentially a chain of trust or a set of signing keys. And then once you have these multiple different trust domains of identities, then you may have scenarios where you need identities from one trust domain to be able to trust identities from another trust domain. And that's where this concept of federation comes in. So that's also defined in the SPiffy spec. So now that we kind of know the terminology and the primitives that power SPIRE, let's talk about SPIRE itself. So SPIRE is a scalable workload identity control plane, and it stands for the SPiffy runtime environment. It's an open source implementation of the SPiffy specification. And at a high level, it distributes two different types of identities that are defined in SPiffy, an X509 SVID and a JOT SVID. And X509 PKI is kind of notoriously difficult to operate at scale. And one of the main challenges there is how do you rotate certificates effectively without too much manual intervention. And so one of the problems that SPIRE solves is automatic rotation of X509 identities. And once those identities are renewed, they're pushed directly into the workload itself. So the workload doesn't need to know that it needs to rotate its certificate. It just gets a new one whenever SPIRE reissues it. In terms of the architecture, I'll talk about this a little bit more in a bit, but it's designed as a server and agent where every host that runs workloads in your infrastructure runs this SPIRE agent component. And then you have a cluster of servers which can be operated in an HA deployment with an active-active kind of HA deployment. And then finally, SPIRE is cloud native and it works across a variety of environments. So this is really what differentiates SPIRE among other kind of PKI systems, is that it's extensible and it works across a variety of different environments and for a variety of different types of workloads. So it's designed with this plugin architecture that allows you to extend SPIRE for your own environment, your own use cases. And there are several different types of ways that workloads can be identified with the built-in plugins. And so those kinds are the Kubernetes, pods, Docker containers, or you can run native Unix processes like on Linux or Mac OS or BSD. And then we also support natively several different environments. So kind of the big public clouds, AWS, Azure, GCP. And then private cloud can be supported through a variety of different plugins as well, including a TPM plugin. And then finally, we have like a native integration with Envoy. So if you use Envoy in your service mesh, SPIRE agent provides an implementation of the SDS API, the secrets discovery service, which will allow Envoy to essentially operate as like a mutual TLS proxy. So going into the architecture a little bit, so I mentioned before we have this server and this agent component. And start with the server kind of exposes two high-level API services. There's a surface called the registration API, and registrations are essentially ways to designate what a workload looks like in terms of its runtime attributes and what its identity should be named, and that's the SPiffy ID. And so those registrations can come from humans through a CLI or through API calls and some sort of programmatic integration with like an orchestrator. So say, for example, like an orchestrator launches a workload, as part of that orchestration of the workload, it goes and registers that workload with a SPIRE server, and then SPIRE server can distribute that registration and identity to the agents that are connected to the control plane. So the second set of APIs here that are worth mentioning are the node APIs, and those allow the agents to securely connect to the server and identify themselves before being able to be part of the control plane. And then once they're connected to the control plane, they can fetch all the identities that are authorized for that agent. So you can group identities to only be available on certain hosts so that not every identity is available on every host. And then finally, the workloads, when they come up, they need to get an identity from SPIRE agent. So they connect to this workload API exposed by the agent, which is a local gRPC endpoint. And it's an unauthenticated endpoint. And essentially they just say, hey, you figure out who I am, give me my identity. And so the agent has to discover who that process is and match it to registrations that it knows about from the server. So I'm going to now jump into a demo, and I'm just going to quickly move over to my terminal to launch the demo, and then I'll jump back here to explain what we're doing. So at the top terminal window here, I just have a deployment script, and essentially this is just starting a Minikube cluster, and then it's deploying all the different components involved in the demo. So I'm just going to kick that off now, and then we'll jump back to the deck. Okay, so this is kind of an overview of what we're demoing here. So these are kind of the infrastructure components involved. So we've already talked about SPIRE server and agent. In this deployment, I have a SPIRE server using a local SQLite database, and it's deployed as a stateful set. So when it receives requests to process registrations, it puts those in its SQLite database, and then SPIRE agent syncs those, and it's deployed as a daemon set. And then there's this other component I've deployed called the Kubernetes workload register, which is available in the open source SPIRE repository. And this is basically an integration between Kubernetes and SPIRE. So it'll listen to different events about pods on the Kubernetes API server. And when it detects there are new pods or changes to pods, then it will go create or update registrations in the SPIRE server for the identities for those workloads. So this is kind of like the base infrastructure that is being deployed. And then on top of that, I have a couple of sample apps that I'm deploying. So if you start at the bottom left here, this is like a deployment event here. We're deploying these two applications called the Hello Server and the Hello Client. The Hello Server is just exposing a gRPC service with a method called say hello, which is just a unary RPC. And the Hello Server requires that clients connect to it with the client certificate. And that client certificate needs to be a SPiffy X509 SVID. So it's going to do some TLS validation. And then the Hello Client is just an application which just polls every 5 seconds on this say hello API. So if you look through the full set of sequences here, we've deployed to the Kubernetes API server. The Kubernetes workload registrar picks up that event, and then it goes and registers the Hello Client and server in the SPIRE server. SPIRE server saves that to its database. SPIRE agent, in an eventually consistent way, fetches those identities. And then the Hello Client and server app, when they're launched, they connect to that workload API in the SPIRE agent to get their identity. And then the Hello Client app tries to connect to the Hello server and call this a Hello RPC. Okay, so now I'm going to go and jump back to my terminal and show how this is all working. So you can see here that the script is completing now, and we've already deployed SPIRE server. So there's the Kubernetes commands for that, and it's come up and it's running, and I'll show that state in a second. And then the SPIRE agent has been deployed as well, and that is now running. And then we've gone ahead and created the SPIRE Kubernetes registrar. This is building the application. And then when this is done, I'll show you the state of the Kubernetes cluster. While this is finishing, on the bottom terminal here, I'll show the output of this in a second. I just have this script, which is just connecting to the Minikube cluster, and it's just going to print out the logs for the Hello server and the Hello client. So you'll get to see like what is actually happening when those apps get launched. We'll just give it 1 second, probably because I'm sharing, it's taking up more CPU.
Let's see if the demo gods are with you today.
Yeah. Okay, so now it's gone ahead and deployed these components in the Minikube cluster. So I'm going to go ahead and just show the state of the cluster. So these are the infra pods that I showed in the first slide. And then here's our Hello client and our Hello server running. And then I'll go ahead and just run this script to show the logs. So let's start with the server logs. You can see initially it's trying to pull that workload API to get its identity, and the SPIRE agent is eventually consistent. So eventually it does get its identity within a few seconds. And then it starts its server, and then you'll see it starts to receive some calls from this client. And this is the SPiffy ID that's present in the client certificate. So this is what the Kubernetes workload registrar registered for that Hello client. And then you'll see kind of a similar story on the client side. It's trying to get its identity. And then finally, when it does, it sets up this mutual TLS connection with the Hello server, and it starts pulling. So that just kind of shows an end-to-end, like how applications get their identity and how they're registered. Okay, and then just a brief, like what's next. I won't go through all these items, but some of the key ones here, we just landed an upstream integration with Istio last week. So this should be available in an upcoming release of Istio. So this is kind of exciting. You can run a SPIRE deployment and use that as your workload identity provider in an Istio service mesh. We're working on supporting SPIRE workloads, or we're working on supporting workloads, obtaining identity from SPIRE in Windows. Today, we only support Unix-based OSs like Linux and Mac OS and BSD. And then we're working on some other exciting things like force rotation of all the keys and certificate authorities in your chain, and then some supply chain provenance integration with SigStore. And we're available on SPiffy Slack here at slack.spiffy.io. These are our links to the SPiffy inspired projects. And on the left here is our spiffy.io website where you can learn more about SPIRE and SPiffy. Cool. So go ahead and stop. Do I have time to answer questions?
Maybe one question.
Okay. Let's see. I see a question. How about supporting other mesh like Linkerd, Kong, and Traffic Mesh with SPIRE? Yeah, we haven't invested specifically in integrations in those service meshes yet, but if you have a use case there, we'd be excited to talk about that. We primarily have been focused on Istio since that seems to be the service mesh that has gotten a lot of traction recently. But certainly we know that other people are using Linkerd and Kong, et cetera. So yeah, please engage with us on SPiffy Slack if you have some requirements around that. We'd love to talk about that.
Yeah, maybe drop that link in there.
Yeah, I will do that.
Cool. Thank you, Ryan, for the short and informative session. Next, we have Steve Sloka, a software engineer from Pittsburgh and currently working at Pulumi. He's dealing with all things cloud, containers, and Kubernetes. He's also part of Kubernetes contributors from early 2015, I think 14, from what I remember. So he's also a maintainer of Contour project, the famous Ingress controller. We'll be talking about Contour in this session. Steve, take it away.
All right, thanks. So yeah, thanks for coming, everyone. Again, I'm Steve Sloka. I'm one of the maintainers of Contour, and today I have I'm using a title I used on another talk called Little I Ingress, Gateway to the App. So 10 minutes, I'm just going to give you an overview of Ingress and Contour and kind of give you enough to like get started. There won't be enough to meet all your needs, but at least we'll again introduce Contour if you haven't seen it and just get you into the mindset of what Contour is. We can skip this. Again, I'm Steve. I work for Pulumi now, but I'm still a maintainer on Contour. Quick overview of what I'd like to talk about real quick is just, what is Ingress, just to level set the room. We'll talk about an Ingress controller and kind of how it works, what the components are, and we'll focus specifically on Contour. And then we'll talk about 3 different ways to configure Ingress, and that's Ingress, a CRD that we wrote, and then a new upstream set of CRDs called Gateway API. And then maybe I'll do a demo, which won't be all that exciting, but we can at least do it and curl some endpoints. So in this talk, I'd like to start with this XKCD, which talks about, hey, there's 14 standards. This is ridiculous. And now there's 15 standards. And that's kind of the story of what we'll talk about with Ingress and kind of how we've gone from, Ingress beta, V1 beta 1 to Ingress V1 to, what we have now. So what is Ingress, right? When we think of Ingress generically, it just means incoming. So I can, ingress into my house that's coming through the front door. The opposite would be egress, which is leaving traffic. So the idea here is we want to have traffic from outside of our cluster come in and hit some sort of endpoint or service in that cluster. It doesn't have to be the internet, but that's the typical example that we use is the internet. So why do this, right? There are a number of ways you could expose applications from Kubernetes. You could use a service type load balancer, which would spin up some sort of cloud resource that would, have an endpoint that's publicly available. Traffic hits that, and then it can hit to your application. Certainly, that's a total use case you could do if you wanted to. You could expose host ports, which is probably bad because you're mapping, ports on the nodes of your cluster to, to the hosts and exposing that way. That can work, but you can only do that once. The second app that you need to deploy can't do that. And node ports themselves are, all dynamic, so that's difficult as well. So Ingress itself gives you traffic consolidation, so you can take all those different applications and consolidate them into one, one entry point. So have all of your traffic hit this one Ingress controller. You get TLS management, right? So now that you have all of your traffic hitting one endpoint, you can now, serve certificates from one place. You can rotate those certificates and do it once. You don't have to deal with, multiple different applications and different timeouts and different settings. You can have that all there. Certificate delegation is a Contour specific feature, which we'll get to here in a second. And then Ingress itself lets you abstract yourself away, right? Your application doesn't have to know what a service type load balancer is and how it's getting configured and how traffic's getting routed. All it cares about is that, I'm going to deploy my application, and these Ingress resources are going to describe how traffic is going to get to my cluster. All this is made possible through this L7 or layer 7 type load balancer, which typically all Ingress controllers are. And that gives you this idea of routing on a domain name and a path, right? So a layer 7 proxy can look at the domain name, so it can say, oh, I understand stevesloka.com is different from google.com, is different from foo.com. And it can look at the path and headers and all the different bits of that application request and make decisions about it and route it throughout your cluster, right? So you get that higher level type router, which lets you make this very, very dynamic. So Ingress controllers themselves, this slide here will show what Contour looks like. But generically, you could swap out these boxes for any other kind of Ingress controller. So again, we have traffic from the internet hitting some sort of load balancer. That job is to balance traffic across your fleet of proxies. In Contour's case, we use Envoy. Envoy is our reverse proxy, and it does all the heavy lifting of routing traffic over the wire. Contour is actually the control plane for Envoy. So when Envoy starts up, we pass it enough config to say, hey, here's where Contour is in the cluster. And from there, Contour will watch the cluster for all kinds of resources. So it looks for services and for endpoints, Ingress objects to configure these things. And it passes that information down to Envoy, and then Envoy will serve that request. So Contour doesn't handle any traffic. It just handles essentially the configuration for Envoy. So the first thing I want to talk about is Ingress, right? Ingress came out years and years ago. It was beta 1, V1 beta 1 for a long, long time. And they just recently made this a V1 resource. It was sort of like the whole world was using this V1 beta 1, so it was difficult to change. So they decided to make a V1 resource and ship that as a stable API. And then they're going to move on with some future things, which we'll talk about here in a second. So this is what the spec looks like. It looks a little different than V1 beta 1 if you're familiar with that. But we've got a name and an annotation, and then here's your layer 7 type routing, where we're routing on a path as well as a domain, which we don't see here. So it's going to route for all domains. So in this example, if request to /blog, which matches the prefix type path, is going to route to this application called blog site over port 80, right? So pretty standard. Again, this is just the configuration that describes how traffic should route. And then you can apply an Ingress controller, which can read this, and then that actually does the actual routing of your cluster, right? So this is a part of that abstraction that we talked about earlier. So what are the problems with Ingress, right? Well, it's a specification, right? And this is a talk from Dave Cheney. Dave Cheney started Contour back in the day, and I joined him as you're back in the Heptio days. But at its core, Ingress was very simple, right? It didn't have a lot of options to define. It was basically like, hey, I want to route traffic from here to there. But the reality of life and the reality of applications is that networking is much more complex than just routing from A to B. There's request timeouts, there's application headers, there's rewrites, there's all kinds of things. And what this turned into is we had lots of annotations to describe all the things that weren't in the spec, right? And the spec was, literally a set of structs. And this is not throwing shade or anything at the folks who built this and designed this. It was just a limitation of kind of what it was. There's always a trade-off with simple APIs. Simple APIs are very easy to consume, but they're difficult to extend and do the functional things. And the opposite, where you have very complex APIs that can do lots of different things. They're very flexible, but then they're harder to configure, right? So you've got to find that balance. Ingress v1, just this level set here as well, as it added a few things. It had a path type field, so that was the how paths should match. Were they prefix or the exact matches or a regex match? It had an Ingress class resource, which again typically was an annotation, but this lets you deploy multiple controllers in one cluster. And then this class will tell you, hey, this resource should be serviced by this type of class with this type of controller. You also added wildcards. Other than that, those three things and some struct changes, it all kind of stayed the same. Now, given these things that we've talked about of these limitations and these things that we struggled with was, the Contour team themselves came up with this set of series called HTTP proxy. And what this was a goal to support multi-team clusters, right? So the reality of life that we saw back when we built a lot of this at Heptio was that folks were lots of users were managing these clusters. And we needed a way to safely manage that Ingress resource, right? And we did this idea of delegation of routing, right? So you can have these root Ingress resources, and then they can delegate parts of those paths off to other folks, right? So I can say, hey, you work in this namespace, you get to own this part of this request path so that only you can configure that. So if someone else comes through and tries to configure that, this basically resolves the conflict that comes out of that. We also wanted to find a way to find sensible homes for common things. So service weights, load balancing strategies, all of those things we talked about, which weren't defined in the Ingress spec and are today annotations, we put those in a proper place in the CRD spec. And this idea of delegation of secrets, this came out because with Ingress, your TLS certificate has to live in the same namespace where your Ingress resource lives. So what this feature lets you do is let you tuck away your secrets and your keys somewhere in some secure admin namespace, but let your users reference those secrets from their namespace where they're working out of and not have to actually have access to them directly. So that was the CRD that we wrote, right? The problem with writing your own CRD is it solves lots of problems, but then you're tied to your application, right? So part of this talk is just giving you generics about what Ingress is and how these things work. So if Contour is not your flavor of Ingress, that's totally fine. But the idea is that we want to have a community, right? Kubernetes is built on having lots of people all interact with the same APIs. So Gateway API is sort of the succession of Ingress. It started out as Ingress v2 and then kind of grew to be more than just Ingress, where it's doing layer 4 and UDP and all kinds of other things. So this is my example of Ingress was very simple and Gateway API is a lot more complex. But it has these generic concepts of that you'll see that are familiar from HTTP proxy, because a lot of the Contour team are maintainers of this project as well. And they want to have the same goals, right? So they had this idea of having role-oriented gateways. So resources are based on the role you are in the cluster. And I have a picture here in a second, which will help describe this. They want them to be portable so they can move around and they can reference different bits and parts, be very expressive so that you can get rid of those annotations, have a proper place in that spec for these things, and be extensible, right? For Ingress, where we ended up adding annotations to extend it, provide ways in this spec to let you reference your own resources and make it bigger. Here's a quick picture of what this might look like. We just talked about with those different roles. So you can see where the application developers and cluster operators and providers all can own different parts of this stack. In some places this may be all the same team, but in other places this could be different folks. So the idea is let them all work on their different parts of the stack, and all add the value to the application. Here's an example just of how traffic might flow through, from a domain name to a route and that sort of thing. Gateway API breaks these things up into different components. There's gateways, gateway classes, there's routes, there's TCP routes. There's just a lot more to this, again, to solve the same thing. So real quick, I think I have like a minute. I'll just show you real quick. If you're interested in how this stuff works, there's a guide here in the Contour site, which explains a lot more of this kind of stuff. And if you want, we can go ahead and deploy this, which will create Contour. It'll play a gateway and all the CRDs that you need. So now if I go ahead and get pods and the namespace project Contour. Yeah, there we go. We can see that we have this running, Envoy still downloading. While that happens, we will go ahead and grab the next bit, which is the sample app, right? So this is going to deploy a sample application as well as a HTTP route, right? So we'll deploy these two things. There we go. So there's our application, and then there's our route that we talked about. So now what should happen is, as long as our pods are healthy, they are. Contour should have seen all those different resources, configured Envoy, and then if we go ahead and refresh our page here, the demo fails. Awesome. I'm not sure what's wrong, but I don't want to hold y'all up anymore. I've got something wrong. So hey, yay for demos. So I'm the failure for the day. So no worries, it happens. So
no failure. Maybe just summarize what you were trying to demonstrate, and then we'll go to Q&A.
Yeah, so this was just showing you was just essentially it was implementing the Gateway API bits. So this was deploying Contour, which are all these bits, deploying a gateway class, and an HTTP route. So that was basically it's demoing how Gateway API would work versus Ingress. So this is the route that it would deploy, and basically said, hey, request to this domain name map to the QWERTY application. So that's all. It was just a silly demo that that followed along with this guide. So if you're interested more, there's lots of links out here on the Contour website as to how Contour works, as well as Gateway API bits.
Cool. Yeah, drop those in the chat.
Right. Thanks, Steve. Definitely, this looks interesting. Solve some of the problems. Okay, I think we have 2 questions on Dapper. Do you want to take it?
Yeah, I was actually just writing in chat. So how does Dapper observability work? So you can configure OpenTelemetry to work with Dapper, and that'll take care of your traces for all of the Dapper APIs. For metrics, Dapper exposes Prometheus endpoints, so you can just use whatever Prometheus distribution you want to scrape the Dapper sidecars and work with those metrics. Another question from Hugo. Do you see new types of building blocks emerging in the future? How about a universal object store to handle CRUD operations against object stores from different cloud vendors or universal graph database operations? So what I showed was actually a universal object store. So Dapper has a state API that you can configure to work against different cloud vendors like Google Cloud Firestore or AWS DynamoDB, and that's basically your global object store, which it adds all types of features on top of. Regarding a graph database, that's interesting. We've actually been talking about this in the Dapper community. We have a GraphQL binding, which you can basically use to talk to all sorts of different GraphQL supported databases. But that's not an API in its own right. It's basically a binding, so you might want to take a look into that. If you want to join the discussion, then you can find it on our GitHub.
Cool. Thanks, Aaron. We have a few more minutes for questions. If anyone has any questions, please feel free to put them in Q&A.
Going once, going twice. Any questions from our panel? Speakers, feel free to ask each other questions if you have any. Not to put anybody on the spot. All right, well, I think we can wrap it up, guys. So I just dropped the link for our next event. And let me go ahead and share that. Can you guys see my screen?
Yeah, we can.
Yeah, you can. Okay. So this is the next event. I invite you to come to this. We might have one more speaker, but I think 3 is probably good for this one. Again, it's the same idea of what we had today. Just kind of short talks and giving you an overview of the CNCF security and compliance projects that are out there. With that said, I want to thank all of our speakers, Jeff, Yaron, Ryan, who else am I missing here? Steve, thank you very much. Really, really appreciate your time. Those were excellent presentations. And yeah, we definitely would not, we couldn't do it without you guys. So thank you for sharing everything. And to our audience, thank you. It's great to see a lot of familiar faces. And yeah, we'll see you next time. Samia, Chakri, thank you so much.
Thank you. And thanks everyone for joining.
Yeah.
Great to hear all these talks.
Yeah, and we'll have, if excuse me, to our speakers, if you could send your presentations, if you'd like, we can share those. And we'll send out the recordings tomorrow, or the recording. Okay, everybody, take care. Have a good day. Bye. Good night.